Hey guys, long time no see. In this video, I'll be showing you a way to measure the thickness of semi-transparent thin films. Typically, you would measure thin films using a method called thin film spectroscopy. For some reasons I'll discuss later, that's not what I'm going to show in this video. If you'd like to learn more about thin film spectroscopy, Sam Zelluv has a great video on his channel. So to start understanding this idea, let's look at a diagram that most of you have probably seen. This is a chart that shows the types of shielding material needed to stop the different types of ionizing radiation. However, this is an oversimplification because it's not just about the material used, but the thickness of that material. Let's focus on gamma radiation, since gammas are really just a high-energy, short-wavelength photon. This is the formula for the amount of material needed to stop gamma radiation. Basically, as a material thickness increases, less radiation can penetrate through it. The rate of absorption is defined by the linear attenuation coefficient, which is specific to each material. As it turns out, visible light acts in almost the exact same way. Instead of a linear attenuation coefficient, we now have an absorption coefficient. The other big difference is the rate of absorption. While gamma rays can penetrate through centimeters of material, visible light can usually only pass through a few microns of most solids. Here's a really simple experiment you can try at home. Take any kind of a chip bag with a metallic inside and cut the bag so that you are left with just one side of it. Then try shining a bright light through it, like the one on your phone. You'll notice that a little bit of light passes through. This is because the aluminum layer inside the bag is only about 50 nanometers thick, so not all of the light is absorbed by the film. This is the same way that a gold visor on an astronaut's helmet works. There is a super thin layer of metal applied, and this blocks harmful radiation from the sun while still letting visible light through. Here's the slide you saw me making in the video intro. Or here's how it looked right after I made it. And here's how it looks now. In my defense, it's moved through two different houses now, and the contrast actually makes this a much more interesting sample. Here's the setup I use to measure samples. First, we choose a laser with a wavelength that will be absorbed by our material. Then we shine this laser on our sample, where only some of the light will pass through. Technically, the glass will also absorb some light, but the amount is negligible compared to a metal film. The light that passes through then hits a diffuser, which makes sure all of the light is measured. Behind the diffuser is a photodiode with an amplifier to boost the signal value. Then you can just use a multimeter, or in my case an Arduino, to measure the voltage from the photodiode. The formula shown above is just a rearrangement of the gamma shielding formula shown earlier. The photodiode voltage with no sample in the laser path will be I0, and the voltage with a sample in the laser path will be I. By entering these into the formula and knowing the absorption coefficient of our material, we can calculate film thickness. Let's take this a step further. We can actually scan the laser across the sample and record the voltage at each point. I just put the sample on my 3D printer and made a code to raster the laser across the glass slide. With a little bit of Python code, we can reassemble all the points into a 2D height map. Here are two samples that I collect the data for. As you can see, the resolution is surprisingly good. The one on the left is just some Sharpie scribbles, and the one on the right is the aluminum coating from earlier. We can take it a step further still and convert that 2D height map into a 3D image. This actually isn't very useful for analysis, but you'd have to admit it looks pretty cool. I measured a maximum sample thickness of about 30 nanometers, which makes sense since we can still see a fair amount of light through even the thickest areas. I mentioned earlier that I would not be using the more common method of thin film spectroscopy. Thin film spectroscopy works by shining a light on a sample and measuring the phase shift of the reflected light. There are two reasons I didn't use this method. The main reason is that your sample thickness needs to be on the order of a wavelength of the light that you're using. My samples are only about 50 nanometers thick, so you need something like an X-ray to measure any noticeable shift. The second, more important reason is that I tried to build one and couldn't get it to work. Finally, let's talk about some limitations for this method. First off, it won't work at all if your sample isn't at least a little transparent. The substrate that the sample is on also needs to be transparent. It might still work if the substrate is reflective, but the maximum sample thickness would be halved since the laser will need to pass through it twice. Sunlight will also reflect off the sample away from the detector, and this will decrease the overall measurement accuracy. I've calculated the maximum thickness you could measure for a few different materials. Additionally, your sample cannot be too transparent. As you can see for glass, you would need about 19 meters to absorb most of the visible light coming through. Thank you so much for watching. I have some really exciting projects coming up, including an automated thin film coating system. If you liked the video, please consider subscribing. And if you have any questions, leave a comment and I'll be sure to answer it. See you later.